Everyone. In today's lesson, we're going to revisit uniform distributions, kind of in an effort we have talked about uniform distributions, but because we're doing things remotely, especially for my in-class group, don't want to move too fast. So we're going to spend some more time talking about uniform distributions. It shouldn't be too heavy today. Let's dive right in. So we've already talked about uniform distributions. We looked at them as far as rolling a dice. We talked about spinners. We analyzed deal or no deal in our game show analysis lesson. A uniform distribution occurs when, in a single trial, all outcomes are equally likely. And we can be a bit more specific, actually. For all the outcomes, X, the probability of that outcome is 1 over n, where n is the number of possible outcomes in the experiment. So when you roll a single dice, that's a uniform distribution because all the outcomes are equally likely. And because there's 6 outcomes, the probability of each is 1 out of 6. In a deal or no deal, when there's 25 briefcases, there is a 1 in 25 chance that each one will contain the $1 million prize. So uniform distribution, all the outcomes are equally likely, but we now have this extra bit of information that we may not have gotten down together in another lesson, is that the probability of each outcome in a uniform distribution is 1 over n. N is the number of possible outcomes. Let's look at a simple example. So here we have a computer programmed to generate a random number between 1 and 5. It's a very simple distribution to make. So let's go ahead and do that. So the 5 numbers you can get is 1 to 5. The probabilities using what we just talked about is 1 out of 5. Sometimes it makes sense to leave it as a fraction. In this case, you could also write that as 0.2. It does give you an exact value. I'm going to leave these as 1 over 5 though. And moving forward, something you may find helpful when calculating an expected value, since you're going to have to multiply in an expected value calculation the outcome times probability, because remember just jot this down here. Remember our formula, our way of calculating expected value is to take the sum of all the outcomes times their probabilities. So sometimes it's actually useful to just do that in your distribution, like when you have a table, because the numbers are just right there. So let's do that. We have a column for that. So 1 times 1 over 5 is 1 over 5. 2 times 1 over 5 is 2 over 5. 3 times 1 over 5 is 3 over 5. And you can see where this is going, 4 over 5. And I'm going to just leave this as 5 over 5. We understand that does equal to 1, but I want to leave it like that for something to illustrate in a minute or so. What does this distribution look like? Well, all of those probabilities are equally likely, and they have a probability of 0.2. So this distribution, this uniform distribution, I believe we did touch on this in a previous lesson. Our probability histogram will just have 5 bars, because there's 5 outcomes, and each bar goes up to 1 over 5, or 0.2. Every graph of a uniform distribution will look similar. But I wanted to go over 2 ways to calculate the expected value. I did show some of these shortcuts in the game show analysis lesson, but I wanted to go things in more detail. So our first method is, just brute force using the expected value formula. Sum of x times p at x. And you can use decimals here, or you can use the fractions. It doesn't matter. So we have 1 times 1 out of 5 plus 2 times 1 out of 5 plus 3 times 1 out of 5. Now, I'm writing out the formula from scratch. We did already do these calculations in our table. Remember, we had a column for that where we got 1 out of 5 plus 2 out of 5 plus 3 out of 5, plus 4 out of 5, plus 5 out of 5. And again, it is kind of useful to leave them with a common denominator, because now you can just add the tops. 15 out of 5, 15 fifths, 15 over 5, and you get 3. The expected value for this distribution is 3. If you've made a table with that last column, you could just start here and you're just adding up those values you got. So that can be the a useful, that can be why doing that is useful in the table, because you just have to add up those results. But we get 3. A second way you can do it with uniform distribution is to use this common fraction of 1 over 5. All the probabilities were 1 out of 5. So you can almost kind of factor it out. So I'm going to use a common fraction of 1 out of 5. Why 1 out of 5? Because that was our probability. So the expected value, everything is being multiplied by 1 over 5. So it's almost like it's a common factor. And what are you multiplying by 1 out of 5? You are multiplying 1 by that, and 2 by that, and 3 by that, and so on. Now that does give you, that's easy to do like mentally. 1 plus 2 plus 3 plus 4 plus 5 is 15. And we get the same thing. But what if we change this question, and what if it was, instead of between 1 and 5, what if it was like 1 to 99? We would do the expected value this way, but adding the numbers 1 to 99 could be fairly, well, it is impractical. So I'm going to share a shortcut with you guys that you may have seen before, you may not have seen before. But you might want to use this for some of the practice for today. It's a shortcut for finding the sum of the numbers 1 up until n. There's a formula. So if you're adding the numbers 1 to 5 or 1 to 10 or 1 to 200 or whatever, this formula always works. What you do is you take the number you're adding to, you multiply by 1 more than that number, and you divide by 2. So you don't need to worry about where that comes from. You can try to show it if you want to show why it works, but that's just something you can make use of here. So for our example, we were adding the numbers 1 to 5. That's 5. 5 plus 1 is 6. Divided by 2. 5 times 6 is 30. Divided by 2, it's 15, and it works out. If you were to do, as I mentioned, 1 to 99, to do the sum, you would just, using this rule, you would do 99 times 1 more than 99, which is 100, and divide by 2. And so you can do that so quick, and you don't have to, slog out a huge calculation. 99 times 100 divided by 2, that's 4,950. So that could be a very quick way to calculate an expected value for a situation like this. So I hope that you jotted down this rule. Super useful, and you definitely will want to make use of that in some of your practice today, especially when you're adding 1 to a fairly large number. In each of those cases, what does the expected value represent? So we got 3. So it's just simply, it's not saying you expect to get 3 every time. It's saying on average, if you were to do this over and over again, you would expect a value of 3, an average of 3. So I might say it's the predicted average of the random numbers, So yeah, I mean, if we did this 100 times and generated 100 numbers, we would expect the average to be 3. All right, we're going to look at one more example here. We have actually analyzed a fair game. Just want to do one more with you guys, again, just to make sure we really have a good grasp on uniform distributions. The previous example we did in an earlier lesson did involve dice. This one involves dice too. This game involves rolling a dice. A player who rolls an even number receives points equal to double the number on the dice. So roll a 2, get 4 points. Roll a 4, get 8 points, etc., etc. If you roll an odd number, you lose 3 times the value of the dice. We're going to see if it's a fair game. Now, you might think, well, obviously it's not a fair game because like you're doubling in one case and tripling the points you lose in another case. And I can see the logic in that. But the even numbers are higher, right? 2, 4, and 6 are 1 higher than 1, 3, and 5. So there's a balance there, right? And we'll see which one kind of wins out in this game. So I've given you guys a table to do this. Here, our random variable is the number of points we get for a roll. If you'd like to pause the video and analyze this distribution, create it, find the expected value, you go ahead, or you can follow along with me. Let's do the even numbers first. Our rule was if you were to roll an even number, you gain double that amount of points. So 4, 8, and 12, respectively, for 2, 4, and 6. If we were to roll a 1, a 3, or a 5, you lose triple the amount of points. So lose 3, lose 9, lose 15, respectively. And, excuse me, this is a uniform distribution. There are 6 outcomes, so we don't need to do any heavy lifting here. The probability of each is just 1 out of 6. And our goal is to find out if this is a fair game. Remember, to be a fair game, you have to have an expected value of 0. Fair game. We want to have e at x equals to 0. And so I laid out 2 strategies for you to do that. Why don't you give that a try, or you can follow along with me here. So -3 times 6, -3 over 6. 4 times 1 over 6, that's 4 over 6. -9 over 6. And again, I know these can be simplified. However, since I'm going to be adding them, it makes more sense just to leave them as fractions over 6. I don't know, squeeze that guy down here. All right, and for my expected value, I just need to add those up. All right, so again, the expected value is the sum of the outcomes times probabilities. And I did those 6 outcomes times probabilities earlier, so I'm just going to write them down. So I had -3 over 6 plus, just want to double check here, 4 over 6. Then we're adding -9 over 6, so subtract -9 over 6, plus 8 over 6 minus 15 over 6 plus 12 over 6. Let's see if we get 0. -3 plus 4 is 1. -9 plus 8 gets me to 0, but subtract 15 plus 12. You actually get -3 over 6, which is equal to -0.5. What does this expected value mean? It means that on average, the player loses 0.5 points every roll. So it's certainly not a fair game. And it's not fair in the sense that it's skewed towards the negative side. So one more example of a fair game for you guys with a few more suggestions for calculating expected values. Hopefully you didn't find the content too overwhelming. I've got some practice for you guys. So for my in-class people, you should have your textbook. Hopefully you brought it home with you. If not, that's okay, because I have tried my best to, I have a textbook with me and I've took pictures of the questions and scanned them and try my best to keep that neat and organized for you. So whether you have the text or the handout, you have these questions there. give them a try. There's lots of practice for you to do. So my plan for Monday, today is Friday. I feel like I've given you guys I've made three lessons in 3 days, and I'm not sure as far as the pacing, especially for my in-class people goes. I obviously I can't talk with you, or I haven't talked with you, so I'm not sure how the pacing is going. So my plan is to just not make any new content for Monday. On Monday, I'm going to make myself available. Well, I'm available all day, but specifically, I'm going to be on my computer just doing some work. But I'm available for help. I'm going to say from 9 a.m. to noon. If you want to send me an email, I could do that, or it'd be great to try doing a video conferencing like Google Hangouts. We're all using the Google Suite for our school. It looks like an A. Email. We're all using Google Hangouts for our school, or the Google Suite for our school accounts. So everybody has access to the app Google Hangouts. And it just would be easier if you had a question or more questions, or an involved question, easier to help you interactively and talk to you than just like back and forth with an email. Of course, if you want to get in touch with me anytime, like please do. Like I want to help you if you're struggling with the material, especially since you can't get face-to-face access. Please let me know. Really love to help you. I know some of you guys are working really hard and staying ahead. If you would like more to do, please let me know. It's not that hard for me to get some extra practice for you to work on, and I'd be more than happy to do that. All right, that's it, guys. Practice hard, keep busy, stay healthy. We'll see you guys soon.